So we're in week 2, and we're kind of finishing up the dating session, and by dating, that's dating the age of the Earth, the age of the universe. But I wanted to kind of back up a little bit and kind of just explain maybe the flow of this class a little bit better, because I think that, we kind of got started a little bit quick and we just jumped right into carbon dating. There's about 5 different areas of criticism that most scientists or people that are intellectual would take against the Bible, and actually against belief in Christianity and against any type of belief. And a lot of people will say, well, do you believe that thing about Adam and Eve? Or do you believe the thing about the Tower of Babel? Or what about that Noah's flood? And I think this class is not designed to be a big science curriculum. It's really designed to take scientific arguments to really kind of discuss those challenging questions that people are going to pose you with. And so the 5 things that we're trying to cover is really, I believe, one of the most foundational issues is dating. In other words, people will say, well, do you believe the Earth is really 6,000 years old or 10,000 years old? Because that's what the Bible says. And that's why we're really covering dating in these first 2 sessions, is really kind of where do those dates come from? And those foundations of dates, where do scientists get them? We kind of talked about that last week, but that's why we're covering that topic. The next topic is, what about all those dinosaurs and fossils? So if the Earth is young, or if Adam and Eve, did they live with dinosaurs? A lot of different questions. Now, these first 3 topics, I would say that John would probably disagree with me on. But I think that it's actually a different interpretation of the Bible is where that comes from, and that's why he's going to be presenting in week 6. The next kind of pillar is, I'm talking about pillars, you'd think I'm Islam or something, is geologic evidence. In other words, so these scientists, they get these rocks, and these rocks have got to be millions of years old. A rock just can't form in thousands of years. And so we're going to talk about how flood geology and how floods can actually create a lot of the sedimentary rocks that we see. The next week is a little bit misnamed. It's called Misinformation in the Textbooks, and it's primarily about evolution. So that's the next pillar, of foundational pillar, that a lot of people will come to you and say, well, what about evolution? I mean, God didn't create people. He didn't create all of these things. They've evolved. They have evolved from microscopic things, and that's just an established fact. And that's actually probably a topic where John and I will agree on quite a bit. I think where and when the creations happened, we'll probably disagree on. But the fact that evolution is really on its way out is probably not a disagreement. In fact, even a lot of secular scientists are kind of getting in that boat. Finally, just kind of the evidence of design. And again, this is something that John and I would wholeheartedly agree on. And that's just, if we look at things now, could they have evolved? Could they have developed gradually? Or do they really show the signs of design? And so that's the flow of the class. Now, there are tons of other topics that will probably come up in question and answer periods and different things. And week 7 is really kind of a catch-all. It's really to kind of address any topic that seems to be coming up over and over again and really address that directly. So this is kind of the tip of the iceberg stuff. You guys have books where you can kind of put some of your notes, and please, if you have questions as we go over a slide, write that down. You guys will also get books, and I've actually got to go back and get the title of the book, but those should be here next week. And there are 2 young Earth creationists, and one is talking about evolution, and one is talking about geology, flood geology, and dating methods. And so as we kind of go through these, if you want to follow along in those books, I'll give reading assignments so that you can really kind of, because in a presentation like this, you're going to get, we're going to go through it relatively quickly, and I don't want you guys to miss out with some of these topics with some guys that have actually dug into them even deeper than I have. So, with that, a review. So this is your pop quiz for today. Can anyone tell me how carbon-14 dating works?
Well, I think one of the examples you talked about last time in the lecture was it was more of a balance between carbon-14 and how carbon-14 becomes carbon-12 and the ratio between carbon-12 and carbon-14 in an animal when it dies versus when they actually get the specimen. And it had to do with radiation the animal absorbed primarily from the sun. And then some of the things we pointed out, well, you had a lot of discussion about baselining it with different species that didn't, like seals, skin samples that were like 300,000 years old or 30,000 years old or something like that. Basically trying to find a way to show that it's very consistent. And then I think another point you made was relating to the fact that the moment something they sample doesn't come as in the date they want, they say, oh, well, that was a contaminated sample. So it's like the moment it aligns with what they want, oh, that's a good sample. So it seems very subjective from that standpoint.
Very good. Yeah, and that's pretty much it in a nutshell. The only difference is carbon-14 actually turns into nitrogen, but other than that, that's pretty much right on the nose. So does anybody, and you kind of already answered this question too, but does anybody remember how well carbon-14 actually works? And you kind of mentioned that it's kind of random, hit and miss. And so the next question, this yes or no, 50-50 chance. Can you carbon date rocks?
No.
What about coal?
No.
It's made of carbon.
Okay. All right. So today everybody's got a bag of jelly beans, or they should have, and we're actually, this experiment's going to be covering two different things. So there's 4 different samples, and nobody took the small bag.
More candy.
More candy. Boy, it's like trick or treat. There you go. Is that all that there was left? Okay, so they're marked. The red and green is to demonstrate carbon-14 dating, and the blue and yellow is to demonstrate uranium-lead dating. If you counted all these jelly beans, and sorry for you M&M lovers, you're not eating those, are you?
Not yet.
You said M&Ms. Sorry about that. You cannot find that many blue M&Ms. I'm just blue or yellow or green. I should have gotten the Christmas M&Ms when they were out. But so there's 4 samples. The carbon-14 old Earth. There's 10 green and 32 red. This is a sample that a scientist would pick up later, and we're going to test this theory, and so we're going to pretend in our class that we're going to age over 30,000 years with the carbon sample. So the young Earth sample it has a lot more carbon-12 relative to carbon-14, and that's to simulate a very light carbon-14 concentration, which is what I believe we had. In fact, I believe we had no carbon-14 at the beginning of the Earth when it was brand new. Uranium lead. Okay, so if you've got a blue and yellow jelly beans, you've got a uranium lead sample. So that's a rock you're holding. It's actually a volcanic rock. And you people with the red and green, you're holding a dead animal, so be careful with that. That makes those red and green really appetizing. So the no lead sample, this is a sample that if a scientist were to pick up a rock today and look at how much residual lead is in it and how much uranium is in it, and assume that there was no lead to begin with, assume that all the uranium decayed to lead, well, that would give them an old age, and that's why it's called the old sample, and that's got the most jelly beans, in case you wondered. And then the sample that's only got the 4 yellow and 48 blue, so it's pretty heavily lead already, and it only has 4 uranium in it. Then there's 4 in a separate bag. And when we talk about decay rates and how uranium and lead work, that'll be obvious why. Now, if you've got yellow and blue, you've got 2 bags. If you've got red and green, you should only have one bag. Okay, so the red and green. The bag of jelly beans is something that just died. Okay, so let's pretend that I've got a clock, and I'm going to let you guys know every 10 minutes to eat a certain amount of jelly beans. So each red jelly bean represents a carbon-14 atom. Each green jelly bean represents a carbon-12 atom. And for every 10 minutes that passes, you need to eat half of the red candies. Now, if you've got the young Earth sample, you don't have jelly beans, they're cinnamon mints. And those only represent a 16th of an actual atom. So this process represents the decay of carbon-14 to nitrogen. So when it decays to nitrogen, the nitrogen goes away. You wouldn't find it really in the sample. It turns into a pretty light gas. And so after 30 minutes, we're going to just end the experiment, and I'll let you know when that is. So at the end of the experiment, and you don't really have to count these, I kind of know, doing the math, how many there should be left. And so if there aren't that many, you did something wrong. But we're going to count the jelly beans at the end, and this is exactly how a scientist would date that dead thing that you find later in life, or later in death, I suppose. Okay, so the blue and yellow. Okay, so we're going to be talking about uranium decay to lead as we kind of do this, and then we're going to probably, after the candies experiment's over, we're going to talk about a few different dating methods. So the sample that you have, now when I say sample, I mean, so if you've got all yellow in one bag, that's the actual sample. The blue is what the yellow is going to turn into. So the yellow represents uranium. It's radioactive, so be careful. And the lead, or the blue, represents lead. So each time you eat a uranium atom, you have to replace it with a blue one. Okay, so every 10 minutes, see, it still says M&Ms, that goes by, eat half of the yellow, and then replace it with as many blue. So if you eat, if you've got them all counted, I think, did I say 48? I forgot what the number was myself. Is it 48? So you eat, okay.
There's 32.
32? Thank you.
Yeah. Okay, so,
Put that in your mind.
but you gotta eat, yeah, I think you eat the green. Okay, so this process represents uranium decaying to lead. Now, lead isn't a light gas, and so it does not leave the rock. It basically stays there. And so this process represents uranium decaying all the way to lead. And so at the very end of this, we're going to test these two samples and see how old they are.
And where does uranium come from?
Where did it come from? So the uranium lead came from a new lava flow. So it's pretty hot. Don't touch it. And it's just sealing. So scientists believe on that new lava that it basically resets the clock as far as the decay rates go. In other words, at least the atoms are locked in, and they're kind of stuck there, unless it were to remelt, which it usually doesn't. So it's a volcanic rock. Now, even though it's uranium that they find in rocks, it's not like those rocks are actually uranium or radioactive. It's just volcanic rock. In fact, you wouldn't pick up the uranium with a Geiger counter in a lot of cases. It's very trace amounts. Okay, so let's pretend the first 10 minutes has already gone. So what do you guys do?
Eat half my red.
Half the reds? Or half the green? Did I say that?
I think for every...
Oh, the reds, right.
I eat half reds, right?
Half reds.
Yeah.
Okay. Well, you guys are happy with candy. Now I can talk about boring uranium. Huh? You eat half the yellows and replace them with as many blues. And don't eat any blues until after the whole thing is over. And the yellow is pina colada flavor, in case you guys wondered.
Prehistoric animals eat these things?
Okay. So here's how the decay happens, and we're we're actually talking about uranium-238. There's uranium-235. In fact, there's even more versions of uranium than what I've listed here. But remember the half-life of carbon-14 is about 5,000 some years. Okay, well, lead, it lives a lot, or actually not lead, but uranium, it takes a while to decay all the way down to lead. And you can see the picture up here shows that it doesn't just decay right to lead. It actually goes on its way through several different elements in the periodic table before it actually gets to lead. And each one of these are radioactive elements. So they're not stable until it gets to lead. Now, once it gets to lead, it stops, because lead is a stable element. And it doesn't decay anymore.
So can they date it at each one of those?
They can. In fact, when they do this dating, and I'm probably not going to cover this too much, they actually do what's called multiple dating methods. So they'll take a potassium-argon date, they'll take a uranium-lead date, and then they'll try to cross-section them to figure out where the line pretty much intersects. Just eat half the reds every time I tell you. So you're already got to eat half of them now. Okay. So, yes, they can see some of these residual elements in the rock as well. In fact, and then they see other elements that they use for dating, and I'll kind of cover those at the very end. Okay. So the question is, how can you kind of tell how old the rock is? And we've kind of alluded to it a little bit with the experiment, but the scientists pretty much assume that the rock that's formed volcanically, it's an igneous rock, basically reset the clock. In other words, uranium-238 is in there and it's starting to decay to lead. So when they get this rock at some future time, billions of years later, they look at it and they say, oh, shoot, you know, this rock's got so much uranium-238 and so much lead, it must be this old. So the half-life we talked about, it's 4.5 billion years. So carbon dating is used not to establish billions of years. It can only date things that have died, and it can only go thousands of years, tens of thousands. Uranium dating and potassium-argon dating, and there's a few more, they establish billions of years because their half-life is so long. In fact, that's why it's hard for us to find places to put nuclear waste, because it just hangs out for so long. It's basically infinite as far as we're concerned. So you put it in a mountain in Nevada. Yeah.
Okay, so if they came up with a half-life of 4.5 billion years, obviously is based on something. I mean, is that based on assuming that it's a constant state of decay, a rate of decay?
Mm-hmm.
So what if it's not?
It is. And that's one of the critical assumptions. So basically, that's what we're going to talk about now is, first of all, the limitations, just like we did with carbon dating, and then we're going to talk about the assumptions. So you can only really date igneous rocks. So if I find a fossil in a sedimentary rock, I can't really date that rock. It's sand and it's sedimentary. It's not datable. In other words, it has no uranium in it. It just was sediment. It was mud sometime, and it settled. And so I can't really date a fossil using this type of dating method. And I'll tell you how fossils are dated. Probably a little bit today, but mostly tomorrow. Or not tomorrow, next week. Sorry. So it's used to establish very long ages because of its half-life, not recent dates. So if somebody says, you know, this got dated to be 10,000 years old with uranium dating, they probably mean carbon dating, and they've just maybe missed. So what are the assumptions? And just like we did with carbon dating, let's kind of check some of these out. So the first assumption is that the daughter element, and the daughter element in our case is lead. So uranium decays to lead. And so the parent element is uranium, the daughter element is lead. And so if there was no lead at the time that the thing froze, okay, well, you can just figure out how much lead's there, and you could do uranium dates. And so, is this true? Well, no, it's not. So it is a false assumption, and the reason is because you really just don't know how much of the daughter element was in there. Scientists kind of know that, and that's why they try to triangulate dates too. So they'll do a uranium-lead date, and they'll try to do a potassium argon date, and they'll try to figure out where are they consistent and come up with a date that way. But that assumption is false. You really don't know how much of the daughter element was there. And in fact, our experiment, you notice that one of our samples has very little of the daughter element, or actually a lot of the daughter element in it, and that's the one with the blue that's got just 4 yellow in it. So it's already got a lot of lead in it, and very little, and you'll see how that affects the date. So specimens have not been exposed to weather or erosion that erode the parent or daughter element out of the original rock. Yeah.
So this was lava,
Mm-hmm.
liquid,
Yes.
that has hardened.
Yes.
As soon as it hardens, then is it a rock?
Mm-hmm.
Okay.
Yes.
I'm saying rock formation.
Yes. So when it's hard, it's got to be hard, and that's kind of when. So when they say a rock is so old, they mean when it hardened. And so over billions of years, it's just really hard for me to imagine that rock sample has not been exposed to weather or erosion. And in fact, there have been some tests done on this specific thing by some young Earth creationists, and they've really proven that this is actually a big deal. Yeah. Did you have a question?
No.
Just thinking. Okay, so the next assumption is the decay rate of radioactive elements has been constant throughout the history of the Earth. And as we did with carbon dating, you know, we pretty much believe that that's a pretty good assumption. I mean, you can kind of test this in labs. You have this sense that, okay, you know, so much of this uranium's decaying to these different elements, and so, you know, this must be a consistent philosophy, even though we're not going to be around a billion years to see it all happen. You know, the rate's pretty consistent. So let's kind of see how this works. And it seems like a good assumption on the face, but I think we'll look into this a little bit more. This picture is actually from Robert Gentry's website. He's actually got a 2-hour-long video on this if you want to see the long version of what I'm presenting today. But so basically, there's something that happens. You know, this decay rate, every time that it goes to a different element, a helium atom is formed in the decay process with the beta and the alpha decay. And so these helium atoms, you know, you got to kind of ask yourself, well, where do they go? And there's a group that was actually funded by the Creation Research Institute, and it's called the RATE study, and the RATE stands for Radioisotopes and the Age of the Earth. Sorry, you probably can't read all of that on your handout, but basically these scientists studied zircon crystals that had been dated at 1.5 million years old. And what was interesting about these crystals is that they had a lot of helium in them. Now, if the crystal was a certain age, the helium would have escaped the crystal. In other words, they know how permeable the crystals are to helium. They know how long it would take for the helium to get out of the crystals, and it would take maybe 1,000 to 2,000 years. But the helium is still in the crystals. And so the problem with that is, so why is that really the case? And what their assumption is that they really believe that at some point in time, decay rates were faster than they are now. So if the uranium decayed quickly to lead, that would explain why the helium atoms are actually still in the crystals. So we're going to kind of dig in a little bit deeper and kind of talk about granite. Now, granite is an igneous rock, but it's considered a metamorphic and igneous rock. Metamorphic means you're just smushing a lot of stuff together under intense heat and pressure. But one of the things about granite that's really key to this whole discussion is naturalists, people that believe that the Earth formed naturally and with hot magma formed a lot of the original granite that we see, not the granite countertops that you have, but the real hard granite. And in Colorado, you can see a lot of granite extrusions still kind of coming up into the mountains. But this is really ancient rock, by both accounts. So what's interesting about granite is it also has this uranium decay. You can date it using uranium dating. And there's an interesting thing that Robert Gentry, again, whose slides I'm using, has found in these studies of granite. He's found these little halos. And at first you'd think, well, whoop-de-doo, you know. So the interesting thing about, so he'll cut slivers of the granite, and in granite is mica. And mica is very translucent. You can put it under a microscope and you can see these circles. And what's interesting about these circles is the diameters of the circles correspond to the decay energies of each one of those decays that I showed you before. So you can see as uranium decays through its decay cycles 8 times, each time energy is given off and it creates a signature. And these are the signatures. And these are called, if you want to do a web search or anything else, they're called polonium halos. So this is kind of what it looks like in 3 dimensions. So as you kind of see the decay, as it decays from element to element, there's energy given off by these beta particles and alpha particles, and they mark the rock. So the interesting thing about these decays is that, remember we kind of talked about half-lives, about uranium getting to lead, it takes 4.5 billion years. So if you look at these decay rates, I don't know if you guys can see that well. So uranium-238, alpha particle, takes 4.5 billion years to decay to the next level, which is thorium. Thorium takes 24 days. So it only lives for about 24 days, and then it decays to protactinium, excuse me, and that's 1.2 minutes. So each one of these shells is not 4.5 billion years, it's actually very quick. And so then you get to uranium-234, 250,000 years. And so each one of these decays, it lasts a little bit different time. And how do they know these decay rates? The same way that they know uranium is because they see the element. They test how much of it's there after a certain amount of time, and that's how they calculate these decay rates. Now, the decay rates of some of these quick ones, 1.2 minutes, 26.8 minutes, they don't hang around for very long. And so, why does all of this stuff matter? Yes?
Okay, so I know gamma is like 0, 0. So wouldn't that happen in all of them? So I was just wondering why there's like gamma on some of them and not on others in the chart.
There's gamma,
Yeah. It's
alpha, and beta.
Yeah, like, I know gamma is like, it's like 0, 0 or whatever.
Like,
I don't know. There's like
Yeah.
a weird like fish thing and then there's like 0, 0.
uh-huh.
But then I was wondering, because from what we've learned in chemistry, like our science teacher told us that it like happens in every decay, like radioactive decay. So why does it just have gamma on like some of these in the column? Like is it just
Yeah, there are actually different particles that are released on different types of decays. And so there's alpha, beta, gamma, but they all leave the same signatures. And they all result in helium as a byproduct. I don't know if that really answers the question, but it is something that you should pose to your teacher and say, hey, look, you know. So the interesting thing is if the magma formed the rock, and it takes a long time to cool magma. In fact, evolutionists believe that it took 100 million years once that the Earth was hot molten rock to cool down to rock. And so if that was really the case, if it cooled down slowly over time, these halos wouldn't be evident. And the reason is because it's liquid. I mean, it's not gonna hold that thing. And if it did, you'd kind of see like these little squiggly lines and it'll all be warped. But these are perfect circles. They're perfect spheres, signatures that are left in the rock. So what we're seeing, oh, and by the way, you gotta eat again. Sorry. So, you know, the idea that the uranium decay rate is constant, I mean, I think, you know, without some of this other evidence, I would have thought, yeah, you know, that makes sense to me. but with some of this evidence, I mean, I really believe that that's just not true, or that it's really difficult to believe that it has been constant. Oops. Now, if you look at a creationist perspective, if God created this original rock, which now creationists believe that it wasn't really necessarily hot magma, and when I say creationists, I'm talking me more than anybody else, that you would see these halos created because God would have created the rock, formed it instantly, and who knows what kinds of scientific things that was what was happening there. But these radio isotope halos, these polonium halos, these are published in scientific journals by Robert Gentry. Yes.
How big are these halos?
Oh, I don't know. I'd have to actually go back a few slides. It showed, but they're very small. So you're seeing them in
Atom
microscopes.
size, or-
By the microscope, I would say that they're pinhead sized, but I don't know. I'll find out.
Okay.
Yeah, because that view that you saw of all of those halos,
uh-huh.
that was actually being looked at through a microscope, and I don't know what kind of
Or
magnification.
power or what.
But yeah. So these are pretty much documented, and a lot of traditional scientists, there really isn't, at least I have not heard a good reason for why these would be there. There just really isn't. And scientists can form and they can create granite in a lab, by the way. So they can make granite, and they can simulate a lot of the processes that the Earth uses. Now, it's not obviously real granite. It's like making a simulated gem, but they can make it, and they can't create these. So it's just something that is really a big mystery.
They can't create the halos?
They can't create the halos.
Do you see those in other rocks or just the granite?
I've only heard about it in the granite, and I don't know if that's just because of the mica, or they can actually see them better, but I can actually check to see if they've found it in other things. And like I said, Robert Gentry, if you do a Google on his name, he's got a website and he's got a 2-hour-long video that kind of goes through the entire process, and you'll see these same pictures. So basically, if we look at kind of how we're doing on our assumptions, in this case, at least with carbon dating, there was one that kind of seemed like it was a good assumption, even though I don't think that that's a legitimate dating method. Uranium lead really has difficulty, and it's really, so we kind of talked about how hard it was to calibrate carbon dating. So to find an artifact, a dead animal or a dead leaf that you knew, for instance, was 5,000 years old, then you could say, okay, let's calibrate our carbon dating testing methods on that thing. It's really hard to find something that you know is billions of years old. I mean, because we just weren't here. At least I wasn't here. I'm pretty sure most of us were here. So let's kind of look at how radioactive dating works. Now, this is actually a potassium-argon date, and potassium-argon is a very similar dating mechanism. So potassium decays to argon. And there was basalt from a Mount Etna lava flow. It was 122 BC. They know that. They know when it erupted. And that dated at 250,000 years old. So basically on the potassium-argon dating, it dated much older than it actually was. A newer volcano, 1801, in Hawaii, the lava dated, actually not the lava, but the hardened lava, dated 1.6 million years old. Again, potassium argon. So one of the interesting things, and if you were to talk to some of the people that defend or kind of argue against these anomalies, they'll say, well, yeah, but lava really picks up a lot of aggregate, and you're really not testing the lava, you're testing some of that aggregate that was really old. So the lava erupted up through the earth, it picked up all of this old rock with it, and those are the dates that you're actually picking up. So I don't I don't think that's really the case. And these are not just things that I kind of picked up from crazy sites. I mean, these are actually scientific letters that are documented, and people debate them.
Doesn't that kind of go with the lava eruption resets the uranium then? I mean, because if it's a newer volcano and it's saying it has more
Right.
uranium left in it, then it would seem to suggest that
Right.
the uranium is
That you're resetting it.
right.
See, and that's, so if it's a new lava flow, it should date young. I mean, because it's just brand new. If it's picking up this aggregate as something, well, that aggregate may not melt into the lava, then you date that instead, and then it gives you an old date, is the theory. So,
Is that
and-
true though that it wouldn't melt in the lava? I mean, if it picks up this aggregate, is it true that the rock wouldn't melt
yeah,
in the lava flow?
there are rocks that don't. So it'll pick up, depending on the melting point of the rock, and you'll even see this if you look at a hardened lava flow, it'll kind of have little bits and pieces of something in it that just, for whatever reason, the lava started cooling by the time it picked that rock up, and it just kind of stuck in there. And you'll see the same.